students. Today I would like to present to you a little program that might help you understand this tricky part of topic 5 on recursive functions, which has to do with the enumeration of recursive function and how you can associate a recursive function with a specific number. Each recursive function can be attributed a specific number, and this leads to the notion of enumeration, and then from there we can also see how some functions are not mere recursive. So in other videos I talked a bit more about the Ackermann function. Here we will talk more about this diagonal function that is not primitive recursive. But I thought that a lot of this topic is very abstract, it's very theoretical, it's on paper. I thought it would help maybe to have a little Haskell program to present concretely how it works, even though we're not going to go into the detail of the implementation of this program, but just to show that this is actually really concrete and not just theoretical. We can actually play with those concepts, and we can actually create this encoding of functions into numbers and decode the numbers as well. Right, so hopefully this will help. So I have this little program. I'm going to start GHCI and load it, and so what it does is that there's some functions to compute prime numbers, and then like it says in the material for this course. We can, using prime numbers and exponentiation of prime numbers, we can actually encode some information and retrieve a very structured information. Okay, so the idea is to say, well, if you have a certain coding, you're going to use the coding as exponents of a series of prime number, right? So if you want to encode, for instance, the sequence, 1, 4, 3, you can just create that code 2 to the power of 1 times 3, the next prime number to the power of 4, times 5, the next prime number to the power of 3. And with a system of factorization, you can retrieve, so that's going to give you a certain number. Here, this number is going to be, so it's going to be 2 times 3 to the power of 4 times 5 to the power of 3. It's going to be, 250. And using a certain system of factorization, you can retrieve from there the number 143. But it's much richer than that, because actually what you can do is that instead of this number being 4, this number here can be also itself an encoding, right? So the 250 can itself be part of a sequence. So say you want to register the code 2 and then 143, which itself means something, and then 5, where you're just going to do 2 to the power of 2 for that number, right, times 3 to the power of 250 times 5 to the power of 5. It's just a coincidence that these are the same. And then when you do this factorization, you're going to retrieve 2, 250, and 5. 2, you're gonna quickly realize that you had the base case. There's no more like factorization to do, but this one you can factorize more into 143. So like that, you can have a structured tower of information that can represent actually functions. And you can see here actually. It happens that this already resembled the structure of the G part of the function the definition of recursive functions, right? You have three parts. One that entails the preceding computation of the preceding number. So anyway, yeah, it's just to explain to you the idea behind all of this. So and how much you can do with it. So that's really what we have here in this little program. We have the capacity to encode and decode, right? So so we have some function codes here, and you can find equivalent things in the PDF for this topic. But I pick different codes, and the coding might not look very intuitive. The reason I put in this specific order is really to try to limit the explosion of the number. So as you can guess, this is a very large number, right? And again, because we work in theory mostly here, we don't care about how big numbers get, right? We just need a number. So we have an unlimited, theoretically unlimited resource of natural numbers that we can use to code our functions. And so so we don't care, but when we implement, we do care, because there's only so much that Haskell can compute with integers. So I try to save as much as I can by reordering things. For instance, here this is a vector, and I put the Sn first before the x, even though in the course the x for the definition of h, it's usually h, x, comma, Sn. Here the vector is reversed because it's more interesting for me to have Sn first. Okay, so there are things like that. But apart from that, it really actually just is a translation of the course into Haskell for the encoding and decoding on function. So the decoding is going to happen through the function u that you can find in the clean theorem. And so this little demonstration is an attempt to try to maybe make more sense of the clean theorem, or at least make it more concrete and visual, right? So how does this work? Okay, so without getting into the details, we can just try to play with it. Well, I define here a few like numbers. So for instance, the number 2, right, is 240. And so it's 2 to the power 4 times 3 times 5. So how does it work? Well, 2 to the power 4, you have to look here. That's basically your encoding table. So 2 to the power 4 is going to be this one. And here what it says, and I'm just going to explain to you, is that I'm going to apply successor as many times as I have arguments here. And because I have 2 arguments after 2 more prime numbers, it's going to apply twice. And now that's for number 3, and that's for encoding number 4. So that's kind of a shortcut I use, try to encode numbers without exploding in terms of natural numbers. Now if I apply my decoding function, that's going to decode. So I apply my function u to 2. What I'm going to get, and I use this little trick to show basically any function, and in my world here, in this domain, a function is always a vector to a vector. Why? Because I need to be able to have a very generic definition of what a function is applied to, right? So the thing is that whether a function is applied to just 0, or if it's, we saw that it can also be applied to, 0 and S0, for instance. Well, this is going to be essentially a vector, and this is going to be a vector with just one element, a vector with 2 elements, but we potentially can have as many elements as we want. And we have the projection function that allows us to pick one element, right? So same thing when we say g of x hxn, and that's also, you can think of it as a vector, right, with 3 elements. So essentially a function is always a vector. It applies to a vector and returns a vector. But that's, so here what it does is that it shows the 4 first instances for this function, for any function. And so whatever I put in, it always returns 2, right? It's a constant function, right? And it's going to be the same thing for 4. It's going to, whatever I put in, I get always 4, right? So this is an ordered pair of input value, output value. So 4, if I apply 4 to, if I do, 4 apply to 0, it's equal to 4, right? And 4 applied to pretty much anything is always equal to 4. Okay, the number 4. I should actually use the this successor 0. Okay. Okay. So so that's for the most basic functions. Now, of course, we can encode some more complex functions like predecessor, for instance. The successor one is very easy because it's already encoded in there, but there's no predecessor function. So for the predecessor function, I'm going to need to use my recursive definition, which is the number 5. Okay, so I'm going to say, okay, I'm going to encode the h, the equivalent of h. Okay, so predecessor here is 2 to the power 5 times 3 to the power of 2 to the power of 1 times 3 to the power of 2 to the power of 1. Okay, and times 5 to the power of 2 to the power of 4. Okay, so what does it mean? Well, if you look here, it's going to mean use that function, which is basically the equivalent of the h. Okay, so that's the h. But then you remember, like, the recursive function h has to be defined through a g and an f, right? So you already know that through the assignment. So the second argument, if you want, this one, is going to define the g, and that's going to define the f, right? So what am I saying here for the g? Well, I'm saying, so the g is, if I zoom on the g, it's 2 to the power of 1 times 3 to the power of 2 to the power of 1. I'm saying, well, take the first one. That's a projection function. Okay. I need to check something. Is that correct? Yes. So g is going to be to be the projection function, and the projection function on yeah, that's true. It's the predecessor function. So sorry about that. I need to go. So what does a predecessor function do? You remember, if you have h x s of n equals g x h x n n. Well, the predecessor function, like I said in some posts, is kind of like an overkill, because all you need to do is really do a projection onto n. So you're going to do a P3 here, right? I mean P33. So you're going to do a projection. You're just going to pick, all you want is to pick that one, because basically, and you don't really care about that. So here what I'm doing is I'm saying, well, 2 to the power of 1 project, and I'm saying project onto, and so the argument after 2 to the power of 1, it should be the number of where I should project. So the thing is that here, in my case, I ordered them in this order. So first I have this one first, and again, the order is just to save natural numbers so that they don't explode too much. This one is first, so this one is second. So that means I need to project to the second one. Here I am doing 3 to the power of 2. Actually, it really doesn't matter. I don't know why this is 3 to the power of 2 to the power of 1, because it should be just 3 to the power of 1. It really doesn't matter. All I want is to say, well, this is not empty. I'm just going to put 1 element. And I'm sorry, bear with me. This is a bit complicated here, but the way I encode it is just to say, well, here, the number of elements, I'm going to add the number of elements plus 1, and it's going to tell me how much where I should project. So I said I wanted to project to number 2. Again, it's the different order than this one. I want to project to number 2. So all I need to do is add one thing here, right? So actually, I decided to just put 3 to the power of 2 to the power of 1. I could have put 3 to the power of 1, which is 3, and it would have been the same thing. But that's also interesting. That means there's an infinite way of describing the same function, and we're going to see that you can describe the same function in many ways. And then so that's our G, and now our F. In the case of predecessor, that's the base case. We just want to say that predecessor of 0 is 0, right? So the F here 2 to the power of 4 is going to be the 0 function, right? 2 to the power of 4 is a 0 function. That's my Z. Here is the 0 function. So that's the vector 0. Okay. Okay. So that's how it works for predecessor, and you can do the same thing for something a bit more complex, which is addition. I'm not going to go through it, but it's basically the same system. Except here, I can't just like pick. I have to pick this big one, the recursion, but it works the same way. Okay. So now, what does it do? Well, I can now do a U of predecessor, and it's going to give me the predecessor of each. So predecessor of 0 is 0, predecessor of 1 is 0, predecessor of 2 is 1, predecessor of 3 is 2, etc. So that's the function predecessor. So the U is going to decode predecessor. Now predecessor itself, think of it, it's a number, right? So that's what is so nice. Okay, so I should have made that clear. The same as 4 is a number, right? 4 is the number 18,480, right? So if I decode 18,480, I get the function 4. Now predecessor is a pretty big number. It's much bigger than and so when I do U predec, I'm really decoding an actual number, right? I'm decoding that number. So if I copy this, I paste it here, it's exactly the same thing. So right, you have to think it's just a numbering system. So now that number corresponds to the predecessor function, right? So we can call it the good old phi number, right? The phi number, the phi of 18917 all the way to 0000 is equal to predecessor. Again, sounds like an overkill. It's a huge number but that works. That's what matters, right? We don't care about being inefficient in terms of numbering, right? And we'll see how we can get a little bit more efficient by starting from 1, using the number 1, 2, 3. But so that's predecessor. Now addition is going to be even bigger, right? So that's the number addition. That's really big, and thankfully Haskell is really good at handling very large number. So that's addition, and same thing for addition. So except addition, it takes 2 arguments. So let me remember, so I don't how I should express addition. No, I don't have it here. I just want to make sure I'm not doing it improperly. It should take a vector with I'm not sure it's going to work like that. It does. Okay. So see addition. So it takes a vector with two. So it takes a vector with two elements this time, because addition adds two elements. So you see the definition of addition allows me to add here 3 plus 2, and I get the number 5, right? And so I can do 1 plus 2 equals 3, and it works fine. Okay. So same thing. I have a definition of addition, but again, U is decoding that number, right? That very, very large number. Okay. So if I want to see how I can decode that large number, I created a factorize function that allows me to, it's not very easy to see. Sorry, factorize 2, I need to add 1, but I can retrieve the definition for the number 2 with the 4, 2, 1 here. And for instance, if I want to retrieve the definition using the number for predecessor, I'm going to retrieve it, like the 5 here is, that's this 5. You should retrieve the 2, the 18 is going to be defined, it's going to be 2 times 3 to the power of 2, so it was 2 to the power of 1 here. So I can retrieve the 1 here correspond to the 1 here, and the 2 here correspond to the 2 here, etc. Right? And then the 16 corresponds to the 2 to the power of 4, the f, which is then further divided into the number 4, etc. So it's you can retrieve the information. It's not very easy, but we can retrieve the information from that. That also shows you a bit more concretely how that works, right? So we have the equivalent of this factorized function that retrieves the information I just showed you, and we use that information to decode the function and apply the function using only the primitive recursive function, right? So that's only, all of this is the definition of primitive recursive function. You have the 0, successor, composition, projection, and the recursive schema, right? That's really basically the textbook, right? And here I just have something to say, well, to put an X if it doesn't match any of those. So if I put a wrong number, right? So for instance, if I say, so again, U240, that works, right? That's the number 2. But if I ask U243, it's going to return XXXX everywhere, because it's just not, 243 is not a function number, right? It doesn't correspond to anything. Okay, so so far so good. I hope that makes sense. That's pretty cool. Honestly, I'm really excited that this works so well. And so that shows you that you can actually make a number correspond to a function for any primitive recursive function. Now let's touch the limits of primitive recursive function. First, we're gonna create some good old phi function that basically takes the first. So again, like I said, we can add like a condition, is good old num here to check, well, is it to sort the numbers that are meaningful and those are not, right? 240 is 1, 243 is not, right? Add the number add. Well, okay, here it's reaching the limits. Oh no, it's not the limits. It's because add it's a bit special. It takes 2 vectors. I mean the vectors with 2 elements. I'm going to take one. I just take one, like predes, for instance. It's going to tell me yes, predes is a good old number. But if I put predes, again, predes is a number, right? Remember? So if I put +1, well, it's not. It's not. likely plus 3 is not either, right? So certain number, only a very limited actually amount of natural numbers are Gödel numbers in the sense that numbers of function, okay? So now what we can do is actually use a Gödel phi function that is going to basically just order them. And so that's going to be the number 1, the number 2, so they're all going to have a number, right? But actually, the number behind that is, you know, the first one that is meaningful is 4. The second one is 6, etc. Right? So if I say, well, just give me the 100 first. Sorry. Oh no, that's I missed dot here. Okay, so that's the 101st meaningful number. Okay, the first 100, right? So 4, 6, 10, all of this. There are many duplicates here, as you can imagine, right? Just the same way that, like I said, predecessor. Here I realize, oh, I could have just put like 1 here. I can actually delete that. And this number, this new definition of predecessor should just work the same way, just fine, right? Sorry, right? It's still predecessor. It still does the same thing. So there are many. So, but what Gödel phi does is that it's going to call this first one phi 1. That's going to be phi 2, phi 3, phi 4, and you have no gap. You basically have a one-to-one correspondence between the natural numbers ordered from 1 and the actual Gödel numbers that correspond to a function via the encoding system. Okay. Okay. Now, that's pretty cool. That's pretty cool, right? But I can also work this out with my vector system, right? So Gödel phi. So Gödel phi 3 is this one. Well, it happens to the identity function, apparently. I don't know for sure, because I know 0 corresponds to 0, 1 to 1, 2 to 2, 3 to 3. There are some, I mean, the thing is that at this level, it's the identity. I only compute the 4 first instances, but there are a lot of them now, just the identity function. Okay. But it's a function, it's a valid function. If I take the corresponding number and I do the factorization, I'm going to be able to retrieve that actual function. Now, the thing is that if you think about it, 3 is also in our world the vector SSS0, right? So I have this other version, Gödel phi v, that is going to take v dot from list. That is going to take one of our vectors. Sorry, check. And actually find the equivalent, right? This is actually basically the same thing, right? These and this. So I now have my my numbering that is included into the sorry, I'm gonna just erase that. Included into our terminology with successor and 0, which means I can actually use that. I can use that phi function as part of our primitive recursive functions, right? So, you know, I have phi 1 equal da-da-da, phi 2, and they all correspond to a specific function, okay? Now, what the function diag does is that it takes diag of x for a certain number, it takes the Gödel phi of that x and apply it to x itself and add one successor, right? So for instance, if I take diag 34, it's going to be that, it's going to return that number, right? And how do I get that number? Well, it's really Gödel phi 34. I'm using the regular number, not the piano number, not the SSS, because it's easier like that. It's going to be this one, basically, right? Apply to 34. So I need to do vectorize 34 because, okay, so it's going to return that. And it's going to add 1 to this. So it's going to take the successor of that. And that's it, right? That's what it does. So diag is a perfectly legitimate function, right? Based on Gödel phi. And we can ask, is diag a primitive recursive function? Actually, I can have a kind of vision of diag v like that, where to 0 corresponds 1. To 1 corresponds 3. So you see it's not just always plus 1. Why? Because for some reason it's not always the identity function, right? So that means that the Gödel phi of 1 for some reason is not, see, it adds plus 1. It's a successor. So that means that here it adds plus 2 because I already had plus 1 here, right? In my diag v. I have the successor, I already had plus 1. So plus 1 plus successor, that's plus 2. Okay, so to 0 corresponds 1, to 1 corresponds 3, to 2 corresponds 3, to 3 corresponds 4, etc. 4, 5, etc. Right? Okay. Now, the question is, so we have our diag function that is such that diag x equals phi x of x. Basically, that's what this means. Plus 1. Right? And so we say, well, if this is a primitive recursive function, diag, then it must have also its number, e, right? It's one of those numbers, right? We must have a phi of e that is equal to diag x, right? Using that system, right? That system of encoding with only those functions, right? Those primitive recursive functions. And the thing is that we here we reach a contradiction, right? Because if this is the case, if there is a number, right? Say it's Gödel phi 107, right? I don't know. Let's suppose it's this one, right? So that means that phi 107 equals diag of x. I mean, equals, phi 107 of x equals diag of x, for all x. Well, the problem is that if I try to compute phi 107 of 107, I get diag 107, right? But in turn, given that definition, this is the same thing as phi 107 plus 1, okay, which is a contradiction, right? Because this cannot be equal to this, right? So we have basically a 0 equal 1, which is a contradiction, right? So so here I mean there's only so much I can show with the program, right? But basically we would need to find the function that corresponds, and we can't find it because there's no such function again, right? That the Gödel phi that corresponds to diag v, and it's why we call it a diagonalization, because if you looked in I mean, we'll look more into diagonalization when we talk about undecidability and non-computability in the part 3. But it's a very important concept that allows us to find a contradiction when we try to fit an element that doesn't fit into a certain class, right? So here we're talking about the class of primitive recursive function, and diag is here, just like the function, the Ackermann function. Okay, so these are non-primitive recursive functions. But this, I'm hoping that this little program make these things a little bit more concrete and visual, to see how this numbering system works, and that it works only for primitive recursive function, right? You define only primitive recursive function, but you cannot. There are some functions you can define. Now, if you add to this list, the mu recursion, the capability to search for a minimum that fits a certain criteria, then it works. Then it works because I can look for I mean, I'm not going to be able to enumerate them like that, but using this minimization, I can look for the first number that corresponds to a certain function, and that's how adding the mu recursion allows us to compute this, right? So it's not because it's not primitive recursive that's not computable. It's a perfectly computable function, but to compute that function, I need the capability to look for a certain minimum across numbers, across unbounded range. Sorry, it's a bit confusing. I'm trying to present a lot of things at once. Really, the objective is not necessarily to get into non-primitive recursive function, but more to understand the notion of enumeration using that system. Okay, it's kind of a bonus to talk about Godolphi and the diag function, but I hope this was helpful. This also should maybe make a bit more clear why we call this ensemble the enumerable set or enumerable languages, and this one is called the recursively enumerable languages, right? Corresponding to the this one, the recursively enumerable languages. This is the language that you can enumerate using your recursion, and that corresponds to the Turing recognizable languages. Okay, it was a lot. I hope this was helpful and somehow fun. I had fun designing that. If you have any question, I would be very happy to answer them.